What's going on, everybody? I'm Will Button. This is DevOps for Developers, and I am really excited to do this video. So if you looked and saw how long this video was and clicked play anyway, first of all, what the hell is wrong with you? But more importantly, thank you. I appreciate it, and I promise this is going to be worth your time, because in this video, we're going to build the complete AWS infrastructure required to launch this new application that I'm building. We're going to build out everything using Pulumi. We're going to build some new resources. We're going to use some existing resources in my AWS account, and then we're going to automatically deploy all of it with CI/CD using GitHub Actions. So let's jump right over to see what we're building, and I'm going to start by showing you what the end product actually looks like. I mentioned that I have an existing AWS account and obviously some existing AWS resources. So let's take a look at what those are. I've got 4 subnets in AWS. Now, 2 of those are public facing and 2 of those are private subnets, meaning that the public subnets can receive external traffic from the internet. So that's where our load balancer is going to go so that it's publicly accessible. And then everything in the private subnet can only receive traffic that's routed to it. It's not publicly accessible, and that's where our Docker containers will be running, because they should only be accessed from the load balancer. Also have an ECR repository in there as well that already exists, so we'll be reusing that in our application here. So if we think about how someone is going to access or talk to our API, the first thing that they talk to is a DNS name. In this case, it's going to be staging-api.leakproof.com. So we're going to create that DNS record in Route 53. And then we also want to ensure that all traffic is done over SSL. So we need to create our own SSL certificate for that domain name. And as a matter of fact, I'm not even going to open up HTTP traffic on port 80. It's just going to be HTTPS only. And if you try to connect over HTTP, best of luck to you. That Route 53 CNAME is going to point to an elastic load balancer. That elastic load balancer is going to be sitting in those public subnets so that it's publicly accessible. And it's going to direct its traffic to our Fargate service. So we're using ECS Fargate to host this. And we've got the existing ECS cluster we're going to use, but we're going to create the ECS service for our application. And then we're going to create a task definition that tells the ECS service what our running environment looks like in terms of number and size of Docker containers and which Docker image to use. So we'll also in this video be building that Docker image, pushing it up to the ECR repository, in addition to creating our task definition. That's going to launch the Docker containers that we're actually going to run in our application. We've got health checks associated with those. And so if anything fails the health check, that container will be pulled out of service and replaced. And then the last thing that we're going to build is a logging facility. So we've got some events in our application that generates logs. Those will be written out by the Docker container. So we're going to capture those logs and send those over to an S3 bucket. And that S3 bucket is going to be the source of our CloudWatch logs data, so that we have one place to go in AWS to see the logs from all of our containers. So that's what the end product looks like. Let's start writing some code and make it all happen. My application is written in Go, so I'm also going to write the Pulumi code in Go as well. So as you can see here, we've got a main.go file open that has a main function with a Pulumi run inside of it. And so let's start building this thing out. The first thing that we're going to do is we have an existing VPC, so we need to grab that so that we can use it. And that's just going to be a string. So VPC-FEFA 7B 9B. That's the VPC of that's the ID for my VPC. And then I also need to grab those subnets that I described to you earlier. So we've got var internal subnets is an array of strings. And then we've got our external subnets, which are those public facing subnets as well. One of the other things we're going to need is I have an existing task role for launching ECS services. That's managed outside of Pulumi. We could manage it within Pulumi, manage it inside, outside. In this instance, I'm managing it outside, so we need to know what that ARN is. And then the last thing we're going to add here is a map of strings, and these are going to serve as the tags for all the resources that we create. And tagging is really useful so that whenever you stumble across something in AWS, you get a little bit of background info about what it is and what it's doing. For this example, we've got a name, which is the API service, what it is, the service that it operates, the environment, its role. So in this case, the role is an ECS service, and the team, which currently is my name. And I did this for a specific reason. So right now it is just me working on this application, but that's going to change over time. And ideally what you want this team tag to be is a group of people you can talk to if you have questions about this service. And so I specifically put my name in here versus a team so that as we grow, anytime someone comes across something in AWS that has me listed as the team, they instantly know that that is a single point of failure because I'm the only person that knows about it and I haven't trained anyone else on it. So that's an indicator telling me that I need to spread this knowledge out and get it out to some other people. And when I do that, we will change the team tag here to be whatever team I've shared that with. The last thing I'll say about tags is I use a specific format. If you look at these letters, the first letter of each one, it's NSERT, which kind of spells insert, just an easy way to remember it. All right, so now we're going to get our VPC. We're going to say parameters VPC error set equal to ec2.lookup VPC. And we need to pass it the context object that we created right up here. And then we're going to get a reference to ec2.lookup args or lookup VPC args. And the only thing we need out of this one is our ID, and that's going to be a reference to the AWS VPC parameter that we created right up here. So this is Go. We have to handle all errors. So if there's an error and it's not equal to nil, we're going to return that error, which is going to cause everything to stop, and Pulumi will give us that error message back so that we can treat that or handle that as we need to. Next, we need to create a couple of security groups that govern the roles for both our load balancer and our Fargate service. So we're going to create the security group for our load balancer first, and we're going to set that equal to ec2.new security group. And then we pass that the context, we give it a name, and then we give it a reference to ec2.securityGroupArgs. And now check this out. You may be thinking, like I was when I first started working with Pulumi, I don't know what the arguments are. So we can do this fill all fields, and then that just fills everything out for us. So let's just take a minute here to talk about what's going on here. We created the new security group. So what does that actually mean? So when you're creating a new resource, there's a lot of things you have to know about it. Most important is what parameters it takes. And the easiest way to find that is I can command click on new security group here. Crank that font up so you can see it. And it tells me right here, new security group registers a new resource, blah, 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 blah. But then it also tells me the parameters that we need for this. Now we know what the context is, and we can give it whatever name we want. This name parameter is what shows up in your Pulumi dashboard. And then we give it a reference to these EC2 security group args. And I did fill all fields, which just automatically populates everything that we can pass as a parameter for those arguments. But we may want a little bit of background info on what each of those are. So again, I can command click on that, and it takes me to the definition for that. And alongside of each parameter that it accepts, Right above that is a description telling you what that is. And so not only do we have the parameter itself here, but it tells me what type of data or what type I can supply it with for the value for that parameter. So that makes it super easy to figure out if you want to build a new security group, what you got to tell it. Now, it doesn't mean that I'm going to use all of these parameters. As a matter of fact, the only ones I'm going to use are the VPC ID, the egress, the ingress, and the tags. Now, we've talked about tags already. That's going to tag the security group with our tags that we defined above. And the VPC ID is obviously the VPC that I want to run this in, which we also defined above. And now look at this. We're doing this Pulumi.string function here. So inside of Pulumi, there's this concept of inputs and outputs, and you've got to tell it what type you're actually working with. It's a little bit confusing at first, but the reason that it works that way is so that as this application runs, it knows about dependencies from other resources. For example, this security group is going to be applied to the load balancer, so you can't actually build the load balancer until this security group is created. And so using this Pulumi.string as the inputs and output types is going to link those together so that everything runs in the correct order. Our egress here, these are the outbound rules allowed by this security group. And so we specify that as an EC2 security group egress array. And then we supply the security group egress args. Those args, again, we can command click on this, and that's going to take us to that type definition to let us know what all of those are and a description of each. But the main thing we're looking here is protocol, we don't care, from port 0 to port 0, CIDR blocks is going to be 0.0.0.0/0, and that's actually a string array with a single element of type Pulumi string inside of it. And this is egress, right? So this means what you're allowed to talk out to. And this block here says you can talk to anything on the internet. Our ingress rule, however, is a little bit different. Again, it starts with a security group ingress array, followed by the security group ingress args. But now this is what inbound traffic we're going to allow. So the protocol, the only thing we're allowing in is TCP, and we're only allowing that on port 443, and it's only allowed to talk to port 443, but it can do that from anywhere on the internet. So what that means is any device on the internet can talk to the device controlled by this security group on port 443. And now when we define this, we defined it. Here's the name. If it generates an error creating the security group, this ERR value will be populated. So we need to check for that. So again, we'll do if error is not equal to nil, return error. That was the security group for our public-facing load balancer. Now we need to create the security group for the containers running in our Fargate service. So we'll do container SG and air is set equal to, again, it's going to be EC2 new security group. Parameters are the context. We'll give it a name, and then we will give it a reference to some EC2.security group args. And I'm just going to paste those in so you don't have to watch me type them all out. But basically, we've got a description that's going to show up in AWS telling us what that is. Egress rules are very much, or are identical to the egress rules for our load balancer security group. Basically, you can talk to anything on the internet externally. Internally, though, the only traffic we're going to allow in is traffic on port 4000. So from port 4000, you can talk to port 4000, and that's using the TCP protocol. And what that's saying is the Docker containers running our API run on port 4000. So that's the only port that we're actually going to open up for them. And then we've got the name of it, our tags again, and our VPC ID. The next thing we're going to build is an IAM role that's used by Fargate to launch our container. Now this is not our task, and now this is not the actual permissions that our task runs with. This is just the task that launches our task, and then it's going to assume the permissions that it needs. Let me show you how that works. So we'll do a task exec role, and our error is set equal to an IAM.new role. Again, we're passing in our Pulumi context. We'll give this a name. It's our task execution role, and then a reference to IAM.role args. And again, we can just highlight fill all fields, and it drops everything that we possibly can fill out in here. So the first thing we need is the assume role policy, and that's the policy that allows this task to assume another role when it starts it. So we're going to use this role to launch the task, and then that task is going to assume the role that contains its final permissions. I'm going to paste that in because this is kind of it's a little awkward to type all this in. Basically what we've got is we've got this huge string here where we actually type in an IAM policy. So this is kind of it's kind of weird to do it this way, but I don't want that to come across as like being something negative about Pulumi, because you see this kind of stuff no matter who you're using for your infrastructure as code provider, whether that's Ansible or Terraform or whatever. There's just so many different things that you have to support. Every once in a while you stumble across one of these. So moving on to standard IAM policy, we define our version, our statement. Key things in here is the effect is the allow the service of ECS tasks to assume role. Our description is a type of Pulumi.string, and it is the IAM permissions for API ECS tasks. Our force detach policies, we're not actually using that one, but we are doing an inline policy. Now, let me walk you through what this is. Inline policies is an array of role inline policies. So inside that array, we have a single item of an IAM role inline policy args. Those args are the arguments to the inline policy, starting with the name of our policy, and then much like we saw above, the policy itself, which is just a big hairy string. And inside of it, we are allowing the action of logs.create log group on any resource. And now that seems kind of weird. Why do we have this policy up here and then this policy down here? The reason being is this is the assume role policy. So that's the role that it's going to use to assume the later permissions. The other part is this is going to use the standard AWS task execution role to launch those services, which for some reason, oddly enough, doesn't include the permissions to create a log group, which meant that we could launch our application, but then we couldn't create the log group that allowed us to capture our logs. So I'm adding it here manually. So we're not using a managed policy or a max session duration, but we do need to give this a name, and that is, again, a type Pulumi.string. And that's going to be task exec role staging. So we're not using the name prefix path or permissions boundary, but we are using tags, and that is going to be our type of Pulumi.to string map, and then we give it our array of tags or our slice of tags. And then once again, we've got our task exec role defined and an error object. So we need to see if that completed successfully. So we'll do if error is not equal to nil. Then we will do what? That's right, return error. Thanks for playing along. Now let's create our load balancer. And remember that there are two parts to a load balancer because we're using AWS application load balancers. So the first part is the load balancer itself, but then also the target group. So a load balancer can have different targets. In our particular application, we're just going to have one target. So we'll need to create a target group for that. But let's start with our web LB and air set equal to ELB.new load balancer. And that takes our context object, right? A name, which is our API load balancer, and then a reference to ELB.loadBalancerArgs. And if we wanted to, we could fill all fields, but through sheer magic, I have everything filled out, so you don't have to watch me type it out. But here we've got our access logs. We're going to give that reference to load balancer access log arguments, and we're just going to drop our ELB logs into an S3 bucket called leak-proof API staging. Internal specifies whether this is an internal or a publicly accessible load balancer. Well, it's not internal if we're going to have people from the internet connecting to it. Name, pretty straightforward. Security groups. Now this is where we use our web security group that we created up above. And so that goes in as a string array. That's a reference to our security group, getting the ID of that, and then casting that to a string output. And then our subnets is a string array pointing to our external subnets, which, let's scroll back up and take a look at that. That was this variable block that we defined here, stating our two public subnets where this load balancer should live. Again, what are we going to do? If error is not equal to nil, return. All right, so that's done. Now let's create our target group. So we'll do webtg air set equal to elb.new target group. Takes a context object, a name, and what does it take? That's right, an reference to the ELB target group args. So we'll put those in. And here we're going to specify a deregistration delay of 60 seconds. This is where we define our health check. So how does the load balancer know which containers are alive and capable of receiving traffic? It does so by checking the v1/health check endpoint on port 4000 of all the targets that are registered to this target group, and it will only route to those that respond with an HTTP 200 response. Finally, we give it a name. The port is 4000 because that's the port that our application runs on. The protocol is HTTP. We give it our tags. Target type is IP. What that's specifically referring to is what type of devices is this target going to point to. It's going to be pointing to IP addresses. Those IP addresses come from the individual containers running in our Fargate service. And what else should we do next? Oh, I know. Let's check if we have an error. And if we do, we'll return that error. So now that defines our load balancer. It creates our target group inside of that load balancer. Next, let's go ahead and create our SSL certificate, because we're using SSL for our traffic, or only opening up SSL on our load balancer, right? So we'll do acm.new certificate. What does that take? It takes a context object and a name of its thing and a reference to acm.certificateargs. We'll give it a domain name, which we mentioned in the beginning of the video is staging-api.leakproof.com. We'll tag that just so it's tagged. And then the validation method is DNS, meaning that this SSL cert is going to be validated by having specific tag or specific DNS entries proving that we actually own that domain. So this involves a little bit of a manual setup the first time, right? Because you got to create those DNS entries, but you don't know what they are until you request this certificate. And it's kind of clunky, but it's okay because the first time we try to deploy this, it's going to fail because this is not a validated certificate. So we'll need to jump over to our AWS console, and you can create those DNS entries just by clicking on Create DNS Entries from within the AWS Certificate Management console. And then once that's validated, we can go ahead and run this again and everything will pass. So kind of clunky to do it one-off, or kind of clunky to do it that way, but it's only a one-time thing. Once this cert is generated, all of our builds are going to run successfully without issue from that point on. And if our error is not equal to nil, I don't know, let's return that error this time. Next, we're going to create our web listener. Easy for me to say, right? That's going to be set equal to elb.newListener. Takes a context and a name and a reference to elb.listenerargs. And the arguments we're providing are the certificate ARN is the ARN for this SSL cert that we generated right above. Our default actions, so a listener has specific actions that it can take. It can take multiple actions. We only have a single action listed here that's of type listener default args. That default action is to route everything to this target group, which is our target group we built up above. And the action type is to just forward all traffic. The load balancer that it's associated with is our WebLB load balancer that we created above. And once again, it's going to listen on port 443 HTTPS traffic using the ELB security policy from 2016 as the SSL policy. And finally, we've tagged that with our tags that we defined up above. Let's see, what should we do next? Oh, I know. If error equals nil, let's just return the error. That seems like a cool thing to do. All right, let's create our DNS entry next. That's going to be the staging-api.leapproof.com DNS entry in Route 53. So the first thing that we're going to need to do that is we need to know what the URL of our load balancer is, right? So we'll do weblb.dnsname, .dnsname. But here's the thing, that's an exposed property of the load balancer object we created, right? But that doesn't actually have a value right now, nor will it have a value when this script runs. That DNS name will only have a value after AWS has provisioned that load balancer and created a URL or a DNS name for it, right? So this is pretty meaningless for us until AWS does their thing. So we need to tell this to hold up and just wait a minute. And we do that with the apply T function. So apply T, it's one way to think of it is if you're familiar with JavaScript, it's kind of like a promise where it says, hey, go do this. And at some point in the future, somebody's going to get back to you on it. When they do this. And the this in this case is run an anonymous function that takes a parameter of a DNS name that's a type of string. And this is going to return a string. And the only thing we're going to do is return DNS name. So basically what that's saying is whenever AWS provisions this load balancer and assigns it this DNS name, run this function here that just returns the DNS name that it's been given, and that's going to populate the value of the LB URL variable that we created. Now, last thing we need to do is say, hey, when you get that back, make it a string input for us, because that's kind of what we need. All right, so now we're going to do our Route 53 record. Oh, look, it takes a context object. And a name. That's cool. And a reference to Route 53 record args, and the arguments we're going to give it a name. This is the actual DNS name that we're using. So staging-api.leapproof.com. The records that we're giving it is, so this can have multiple records. We're only giving it one at this time, but we're giving it that DNS name that we're getting from this LB-URL variable we created up there. Our TTL, what's your DNS TTL? I'm picking 300. The type of record is a CNAME, because it is one named record pointing to another named record. And then the zone ID, this is the actual AWS zone ID for the leapproof.com domain that I own in AWS. All right, so I think that sets up our load balancer, our listener, our target group, our SSL cert, and our DNS name. Let's move on to building our image now, or building our Docker image and pushing that up to the registry. So the first thing we need is a registry. And I told you I had an existing registry, so we just need to look that up using our context and some lookup registry args. In this case, the only thing we need to tell it is the name of the registry, and that's Leapproof API. That again returns a registry and an error, but what about the error? Oh, if it's not equal to nil, return. Now, in order to talk to that registry, we need an auth token. So auth token error set equal to ECR.get authorization token, and we pass it a context, and that's actually all we need to give it here. But we did get an error back, so we need to check for that. All right, with that token, once we build our Docker image, we should be able to push it to the registry. So let's get to building that. So we'll do image and error is set equal to docker.newImage. And that takes, oh look, it takes a context and a name and some docker.image args. Now we're going to fill all fields on this just to give you an idea of what's there. So we're going to give it an image name, which is basically the full URL to my Docker registry in AWS. And then this build thing, this is the actual Docker build command. So we're going to do a docker.docker build args, and we'll fill all fields here. And we're not actually using a lot of them, but I wanted you to see what they all are. The ones that we need are context. That's going to be Pulumi.string, that is .whack. So now the reason it's .whack is because if you look at the project folder here, we're down here in the infra folder. Okay, so technically we're in the infra copy folder because I've already written all this code, but I wanted you to see what it looked like, all right? Fine, you busted me. Regardless, we're down in this folder, but our application folder or our application code is one level up. So we want our Docker build context to operate on that. So we give it .whack to say, hey, go up one level and look for your stuff there. The Docker file is going to be just a path. And again, we're one level down, so we got to go up one level. And then it's actually called Docker file. And believe it or not, that's all the arguments that we want for our build. But since we're here, let's take a look at our Docker file. If I can spell that right. Crank that up so you can see it here. This is kind of interesting, okay? So we're building a Go app, right? So we've got all of our source code, and then we run the go build command, and that generates the binary. So in our final Docker image, we don't actually need the source code. The only thing that we need is that compiled binary. So that's exactly what we're going to do. We're going to use a build stage that starts with the Golang Alpine server. And then we're going to add some stuff that we need in here to make our build successful. We're going to add the contents of our source directory in there. And then we're going to run make build API, which if you saw the other video I did on this project, you know that that make command actually runs the Docker build command and builds it for both my current operating system and builds a version for Linux. So we're relying on that. Now, once that's done, we're going to kickstart a new Docker image from Alpine, set our working directory, and then copy from build env, which is this thing right up here. We're going to copy the file in source bin Linux AMD 64 API to /app/API. So this API thing here is the binary that we built. So that's the only file that we are taking across with us. And then we're setting our entry point to execute that binary. Sweet, right? I thought so. So we don't need a local image name, but we do need to fill in our registry details. So we've got image registry args, which the args that we need are the server, and that's a Pulumi string that is going to be set to our registry.repository URL. Our username is oh look, it's a Pulumi string that is set to our authtoken.username. And then finally, our password is another Pulumi string that is our authtoken.password. And we don't need to skip push. So what we've done here is we're building a new Docker image, giving it a name. Here's how you build it. When you're done building it, here's where you push it to. And when you're pushing it there, here's the server and the credentials that you're going to need to make that work. And that came with an error. So what do? Oh yeah, we should check to see if that's nil. And if it's not, we'll return the error. Next, we need to create our container definition. This is what Fargate is going to use to determine how it's supposed to run this Docker image. And so we're going to do image.imageName, and then again with the apply T thing, because we've got to wait for that image to be built and pushed up to the repository. So when that happens, we want to run an anonymous function that gets a name as the parameter that's a type of string. And this function is going to return a string or an error. And I'm going to paste this in because it's another one of those areas where it gets really kind of hairy. So we're just creating this parameter or this variable called format string. And it's all the values that you need to run your Docker container. So if you've run Docker containers in the past, this stuff's all going to look familiar. We've got a name of the container that we're going to run. The image we set to %q, so we're going to pass that in. We've specified our entry point, so we're overriding the entry point from the application or the Docker image, still running the same binary, but passing it the --env argument and setting it to staging so that we know we're running in the staging environment. Setting up our port mapping, so we're going to expose port 4000 on our container so that we can actually talk to it. And then this part here is where we actually define the log configuration that allow the logs generated by our Docker container to end up over in CloudWatch logs. So that's using the AWS logs log driver. Create the group, sure. If it doesn't exist, create it. The group name to create, leak-proof staging logs. The region, I'm doing everything in US West 2, and then a prefix of API logs. And then we are going to return that just as a formatted string that there's the string that we want to return, but then we also had this variable that we're going to fill in, and that gets populated right here. The last thing, just like we did last time, we need to tell it whenever this happens that this is a string output. Now that we have our container definition, we can create our service, our ECS service. So we're going to call this app task, and error is set equal to ECS.new, not net, new task definition. Give it a context, a name. Let's call it API task because I suck at naming things. And we'll give it a reference to ECS.task definition args. Now the arguments we're giving it, the container definition is the container def that we just created. CPU, giving it 256 CPU units. Our execution role, ARN, this is the IAM role that we created up above that allows this task to start. Family, Fargate task definition, that's required because we're running in Fargate. Memory, give it 512 megabytes of RAM. Network mode, AWS VPC, meaning this is only going to launch inside of a VPC, and it will be issued an IP address from within my VPC, meaning that it's an internal address, not publicly routable. So again, I'm doing that so that no one in any way can ever talk to my Docker containers without going through the load balancer. Requires compatibilities. This is running on Fargate, so we have that Fargate requirement there, giving it our tags, and then our task role ARN. This is once this task launches, this is the role that it's going to run as, which specifies what things it has access to as a running task. And again, if error is not equal to nil, what should we do? Maybe just return the error. I don't know. So that's our task definition. Now we can create our service. So we'll do an ECS.new service, taking in a context, giving it a name, and a reference to ECS.service args. And I'm going to paste these in here because it's a lot. And then we'll walk through what all of them are. The cluster, this is my Fargate cluster I mentioned early on in the video, which is what, 2-3 hours ago by now, that I have an existing Fargate cluster. So we're going to use that. We're not building a new one, although we could build a new Fargate cluster. That's just not the way I like to do it. Desired count, how many containers should be running on this thing? So we're going to start with 1 because this is our staging environment. When we roll this to production, that will obviously be a number greater than 1. It'll actually be a number that's at least 3 or more. The launch type is Fargate. Load balancer. This is the load balancer that it's going to use. We're going to tie these containers into the web target group that we created above. So it needs the ARN for that. Here's the name of it, just what it's called. Our network configuration, assigning public IP. No, do not assign a public IP. The security groups is our container security groups.id to string output. We saw that earlier when we did our load balancer. And then our subnets is going to pass in the value of our internal subnets that we created as the very first thing so that our containers are running without public IPs and they're running within our private subnets, meaning there's no way you can get to them. We'll tag each of them, and then our task definition, this is the task definition that we created up above. The last thing we're going to do here is a comma and Pulumi.depends on, and the resource that it's going to depend on is an array of Pulumi.resource of type web listener. So that listener has to be completed building before we can actually build out this service. Makes sense, right? Because the listener is where they get put. So you got to have that. I mean, yeah, makes sense to me, right? And, you know, I don't want to say that's it, but 287 lines of code later, and yeah, that's it. For this part anyways. So that's going to build out our AWS infrastructure. The last thing we need to do, I told you this was going to be automated. So let's take a look at this file, our push.yaml file. Crank that up so you can see it. I'm not going to type this out because it already exists and I can just walk you through it. This is a GitHub action file. It's in our GitHub workflows folder. It's got a name of Pulumi. And then on a push to the branch of main, run this job, update job. We named it update. It runs on Ubuntu 22.04 and do these steps. So the steps that we give it, check out the code. It's obviously got to check out the code or it's not going to get very far. It's going to set up Go with Go version 1.18 because that's what I'm using. We got to configure some AWS credentials. Pulumi is going to talk to AWS, so it's going to need some creds to do that. It's going to use the AWS actions configure AWS credentials action. And then we're passing in our AWS access key, the region, and the secret access key. And these are secrets that are stored within my GitHub repository. All right, so this little template here just pulls that in from GitHub. We're going to run go mod download to download all of our Go dependencies so that our code can run, and then change our working directory to infra. So remember before I told you about the little folder skipping around thingy here? All of our Pulumi code is in this infra folder. So we need to change into that directory in order to execute our Pulumi code. Makes sense, right? Well, until it fails because you forgot to do that. And then we're going to run our Pulumi actions. We're going to run the Pulumi command up with a stack name of staging because we are running our staging environment here. Whenever we get ready to deploy to production, we'll have one of these that says production. Again, our working directory is the infra folder. And then in our environment, our Pulumi access token, which is just used by Pulumi to update our Pulumi dashboard. So we can commit all of this code, push it up to our repo, merge a branch in, and because we added that new GitHub action, that's going to run this update action here when we merge that in. And if we click on that, you can see all of the actions that we defined here. The main bulk of work here was done under this run Pulumi actions. So we can actually expand that and see the output of the Pulumi command, which something to note here. This is the output of the Pulumi command. So you want to be very careful that you're not returning sensitive data in the output here, because it will be accessible to anyone who has access to your GitHub repo. Final thing that's worth noting here is resources. It tells you what was updated and replaced. You can see on this one updated and one replaced, 2 changes. Now, obviously, we just wrote the code for a bunch more than 2 resources, but as you might have guessed, I've run this a bunch of times, putting all this together, working out all the bugs, and recording this demo. So let's take a look at AWS and see what we built. We've got in ECS, we've got our Fargate cluster, which was that existing cluster we were using. We've got our service name here that we built using Pulumi. If we click on that, we've got our Fargate task definition. Look at this Fargate task definition revision 31. I point that out to show you that this is a trial and error process. You know, I didn't open up my editor, bang out all that code, launch it, and go live. We're actually on revision 31 of me writing code, deploying changes, finding bugs, writing more code, back and forth just like that. Our tasks, we've got our one task running here. And that task consists of one container. And our logs are over in CloudWatch logs. So if we click on that, we should be able to fire that up. And there's some of our logs. So that's pretty cool, right? Let's see, what else did we build here? We built a load balancer. So let's take a look at that. We'll go over here to load balancers. Inside of our load balancer, we've got our listener that we created on port 443. It's also tied to an SSL certificate. If we click on that, it's our certificate for staging.api.leakproof.com. And then our target group that we sent it to, default forwarding to the target group. If we take a look at that, there's our target group with one healthy host, no unhealthy host, and we can actually see, oh look, it's an internal IP address with port 4000 exposed, so no way that it's publicly accessible, right?
All right, so that was a lot to cover, right? But we could still even go further. For example, we built our API. We're going to have to build our production version of that too, but we could also include some dashboards starting to collect metrics from our load balancer and our API responses, put that into a dashboard, have Pulumi build and manage that as well. Same thing with alerts. If we exceed certain thresholds in our application, we could trigger alerts in AWS, and we could use Pulumi to build and manage that as well. And we've also got auto scaling. When those alerts kick off, we might want to scale out the number of containers that we have to handle that load. So there's still lots of work to do on this application. And there's also the reusability part of it as well. For example, if we have multiple applications, odds are they're probably all built just like this, but we don't want to have to duplicate that code every time there's a new application. So one of the things we could do from here is take all that code that we wrote and pull it out into its own module that then could be used in any application and just supply some parameters there. For example, create parameters for the name of the service, how much CPU, how much memory you want, number of containers, and then just pass those parameters into the module that we create out of that. And then anyone on our team building any application could just reference that module, supply the parameters, and boom, they're up and running in AWS using all the constraints that we created. So we would know, as long as they used our module, that they would be using SSL and that their containers would be in the private subnet, and all of those things that someone may not know to do, we're just doing for them. And now that's exactly what we built whenever I was with Aptiv. So any developer on any team could start a new application, supply their parameters file, and then it would just automatically deploy the way that we wanted it to within parameters that they may not even know have existed. Now, we built that a long time ago before Pulumi was up and running, and actually ours was a version of like some bash scripts and some Python scripts and some Jenkins libraries that we created, and some like voodoo and black magic. Matter of fact, I even showed up at the office one day and there was a shaman priest in my office purging it of demons to try and get this thing to run. So Pulumi has made those same features accessible to everyone else without having to go through all of that. And so that's pretty cool. The other thing I like about it is we wrote it all in the same code that the application's in. So any developer working on this application can open that up, and they may not know a lot about AWS, but they do know how Go code works, so they could kind of follow along with what's there. But that goes off down a whole nother rabbit hole that I will save you from if you're still watching at this point. Thank you. I've got a ton of work to do, so I'm going to do that. Make sure you subscribe to the channel if you want to see the rest of how this application comes together, because I'm creating all of it in videos and publishing them here. And then also check out the DevOps roadmap. If you want to learn more about all of these different things that we created and how it ties into all of these different facets of software engineering, the DevOps roadmap is a great way for you to like identify pieces that you know, and it's a choose your own adventure style guide. So you look up something that you know and you can see how it relates to the other things. Go check out those things and see how they relate to other parts, so on and so forth. I really think you'll find it helpful. Check it out. Let me know. If you build something with Pulumi, let me know down in the comments. But I got more code to write, so I will see you in the next video.